last few lectures, we have discussed the utility of regression in bringing out useful information from experimental dataset. We have discussed the technique of simple linear regression. We have seen how to calculate the errors in simple linear regression, and we have seen one example of simple linear regression. Then we have moved toward multiple linear regression. In simple linear regression, we have one regressor connected to one response, and they have a linear relationship. In multiple linear regression, you have multiple regressors and they are connected to one response and they still have a linear relationship. As we go from simple to multiple linear regression, it becomes increasingly more difficult to solve the equation and get the W0, W1, etc. In this lecture, we'll try to find out a compact notation using vector and matrix concept. After we understand this concept, finding this regression coefficients will be much easier no matter how big the list of regressor is. Let us take a moment and revise what we have learned from simple linear regression. We had a training dataset xi, yi, I goes from 1 to n, and the response y is y hat plus a residual. Y hat is our least square estimation of y, which we have assumed for simple linear regression to be W0 plus W1x. To get the W0 and W1, we minimize the cost function yi minus W0 minus W1xi whole square summed over all I divided by total number of data points, that is n here. To visualize the process, we can think of two nodes. One node is the bias node that contains W0, another is the weight node that contains W1. In bias node, the input is 1. That bias node multiplies that input with W0 and send this to the summation node. And weight node, the input is x. X is multiplied with W1, sent to the same summation node. This node sums W0 and W1x and sends that as output. Now let us look into this problem slightly differently. Let us take our input, which is what we see here, 1 and x, two inputs. We can treat them as a vector which has two components, x0 and x1. And usually vectors, unless specified otherwise, are treated as column vector. So I can write it as column vector, or I can write it as row vector x0, x1 transpose. In case of simple linear regression, x0 is 1, so I can write this vector as 1 x1 transpose. Now regression coefficient may also be treated as a vector w, that is W0, W1 column vector, or we can write it as a row vector W0, W1 transpose. Here W0 we call bias and W1 we call weight. Now we can see that this y hat, that is W0 plus W1x, which is the estimation of y, I can write that as an inner product of this vector x and w. The inner product we write as x dot w, or we can write this x transpose w, column vector x. After transpose, it gives a row vector, row multiplied by this column simply gives a scalar. So now let's move forward. We have defined this x vector, w vector, and we have seen this y hat is x transpose w. Now y hat I is xi transpose w, and xi we are defining as 1 xi1. By xi we mean that this is the x1 in ith experiment. So I goes from 1 to n. this is the number experiment. This is the serial number of the experiment. So in experiment 1, our input is x11. In experiment 2, our input is x21, etc., etc. Now if I take vector from ith experiment and then I take a dot product with w, I get the estimation of y, I. Now we define a matrix. In this matrix, I have each of these rows are x1t, x2t up to xnt, and xit is one xi1 row vector. So I can write this as 1 x11, 1 x21, etc., etc., 1 xn1. Because xit will be row vector, xi is a column vector, xit will be simply 1 xi1. And now we can see this y hat, I can put that as a vector, and I can write y hat vector equals xw, where both the y and the y hat, I can define them as column vector, n-dimensional column vector, depending upon the experiment. Every experiment is giving me a value of y, and every y has a corresponding y hat. That is how I am taking them as n-dimensional column vector. So here w is only a two-dimensional vector. So when I multiply this matrix with two-dimensional vector w, that is w0 and w1, then what I get as this y vector is this first element of this y vector will be w0 plus x11 w1, second element will be w0 plus x21 w1, etc., etc. I will have n elements of this column vectors y hat, which is equal to xw. Now we come back to the cost function, that is e, which is a function of this w0 and w1, which means in this case, this is a function of the vector w, which is given by 1 by n summation of yi minus yi hat whole square, means summation of e square. So now what I can write here, that this is this whole square, when I sum it up, it means that if I have a vector y minus y hat, this is a vector, then its elements will be y1 minus y hat 1, y2 minus y hat 2, etc., etc., yn minus y hat n. So if I take this vector and take a dot product with itself, then each of this term will be multiplied with itself, and then all those squares will be added up at the end. Therefore, summation of this square can be written as this vector and dot product with the same vector. So y minus y hat transpose y minus y hat, that is a dot product of y minus y hat vector dot y minus y hat vector. Now we know that y hat vector is xw, so I can write this as 1 by n y minus xw transpose y minus xw. So moving further, recall from simple linear regression that we have discussed before, the e cost function comes as 1 by n summation of yi minus w0 minus w1 xi1 whole square. At that point we didn't use this xi1 really, we were only using xi here, but here we are having x1 as the variable, that is why I am writing this 1, otherwise it looks just the same. So del e del w0, if I take a derivative of this, then 2 will come out of this summation. So whatever there within the first bracket, it will remain there, only square will go out, and then because w0 has a minus sign here, a minus will come here. So minus 2 by n and whatever there within this first bracket. I can write this as yi minus yi hat, because yi hat is this w0 plus w1 xi1. Similarly, del E del W1 is very similar. 2 will come here. Whatever there within the bracket, it will remain there. And then this W1 xi1, I have to take its derivative. So it will give me minus of xi1. That is where this minus sign is here. And xi1 is here. Once again, I can write it as xi1 yi minus y hat I. Now, let us look into this y hat minus y hat I. These are the elements of y minus y hat vector. And this xi1 etc. they are elements of this xt matrix or x matrix. We are using the transpose here. For x, this 1, 1, etc. it goes to first column. Second column is x1, 1, x2, 1. So we are transposing it. So first row is 1, 1, 1. And second row is x1, 1, x2, 1, etc. So now this summation here, I want to write it in terms of x and y vectors. So let us see how we can do so. We want to make this gradient of E to be 0 to minimize E. And this gradient vector has two elements, del E del W naught, that is this one, and this is the second element, del E del W1. We are writing it as negative 2 by n and then xt multiplied by y minus y hat. So how this is meaningful? Let us see. This y minus y hat vector is a vector that has y1 minus y hat 1, y2 minus y hat 2, all these elements up to yn minus y hat n. And then when I multiply with this xt, what I get is this, take this top row and multiply with this column. All are 1 here. So this will be simply the summation of all these terms here. And that is what exactly we see in del E del W naught. Similarly, when I take this second row and multiply with this column, I'll get this x11 multiplied by y1 minus y hat 1, etc., etc. Then its summation. That is exactly what I am getting here in W del E del W1. Therefore, I can write that this vector is equal to negative 2 by n and xt y minus y hat. And then again, y hat is xw. We know it from our previous slide. So this is xt y minus xw. Now we know that minimization requires del E equals 0. And del E equals 0 means this particular expression equals 0. So this xt xw, this term is equal to xt y, this term, which gives us w is equal to xtx inverse multiplied by xty. This is a very beautiful closed form solution of w. Values of this vector w is something that we were looking for. Once we get the w, if we want to get this y hat, this is simply x multiplied by w. So y hat is this particular w multiplied by x. So you can see here I have this x. So clearly this closed form solution, it looks better, it's easier to solve, and we'll see that how to solve it. But let us now first generalize this with k regressors. The generalization would be easy because it will not change anything. Whatever there for two regressors, it will be same for k regressors, whatever it is. So here our model is the multiple linear regression model, w0 plus w1 x1 etc. up to wk xk. And you remember that previously we had to work a lot to get all the equations of w0, w1 etc. So here our regressor, once again we take it as a vector 1, x1, x2 up to xk. Just like previously we were taking 1 and x1, but now we are going up to xk, and weight as a vector w0 to wk. Now we can write this as y hat wtx or xtw, whatever way. This is an inner product. And then for each observation, this y hat I is w0 plus wjxij. J goes from 1 to k, all these k regressors, and I is the coming from the experiment serial number, this 1 to n. So this one I can write as wtxi or xitw, whatever way you write, they mean the same thing. Regressor at each observation, also this xi, that will be a vector 1, xi1, xi2, etc. up to xik. And this transpose of these vectors, we can write xt as rho, xit as rho, wt as rho. This will be w here, w here. All right. So now we also see that the response, they are also vectors, now exactly the way we have defined before. And then we create this X matrix. Earlier this X matrix was only 1 and this first column, but now I have so many regressors here, k regressors, so it will go all the way up to k. So first row is coming from the first experiment x11, x12 up to x1k. Second row is coming from the second experiment x21, x12 up to x2k. So this should be x22 up to 2k. Here xn1, xn2 up to xnk. And then this yi is wtxi as we have defined before, and we can write this y hat is xw. So then the regression problem is finding the least square, yi minus y hat whole square. And here is the same problem. Only thing here is that we have this n by k matrix, X matrix. Once again, we minimize the least square cost function y minus xwt into y minus xw, and we get the gradient 2 by n xt y minus xw. Zero gradient gives me the same equation. So it doesn't really matter that how many regressors we are working on. It could be 1 or it could be as many as it gets. The expressions are exactly the same. So this gives us easier way to solve linear regression problem, no matter it is simple linear regression or multiple linear regression. So this type of closed form of solution, this is how the linear regression softwares also, they calculate this value of W. And this closed form of solution is very helpful and one of the reason of popularity of this least square regression models. We can now go back to the example problem we have seen before, that is the shear strength of rocket propellant with respect to age in weeks. And you remember that we fitted this linear model before by getting into the normal equation of W0 and W1. And solving from the normal equation is easy because this is only a two unknown system. Two equation, two unknown system, solution is very simple. But when it goes for a very large number of regressors, it cannot be very simple. So this was our answers, 17.93 and minus 0.25. Now, if you want to calculate this using this vector matrix technique that what we have learned, then you have to first define this x vector and y vector. X vector will be 1, first column 1, and second column will be, in this case there is only one regressor, so second column will be 15.5, 23.5, etc, etc. Y vector is all the numbers in this third column here in our experiment. Now, this is our xt, transpose of this X matrix, and we can calculate this W directly, xt multiplied by X inverse xty. When you multiply xt and X inverse, your matrix size is small, it's a 2 by 2 matrix, so getting the inverse is easy, and eventually multiplying with xty, you get this 17.937 minus 253 matches exactly with the results that we have got. Now, when the number of regression is large, this xtx will be a very large size matrix, and you cannot just invert like this. In a 2 by 2 matrix, you can get an inverse very easily, but in a large matrix, you cannot. So we don't directly use this expression. What we do is that we solve this, we find this xtx, and then we solve this as this AU equals B problem solving for U. So that way we solve this using some linear solvers that we have discussed before. Now to summarize, we have now implemented linear regression in vector matrix notation. This notation is very useful for large number of regressors. You can use it even for small number of regressors, but its real utility comes when the number of regressors are very large. For your exercise, you can take this X and Y vectors and then manually you calculate this xtx inverse xt into Y. Thank you. That's all for this lecture. I'll see you in next class.